Okay, so to simplify this radical, we need to take everything on the inside we can outside. So first thing to remember for a radical is if there's no index in the top of the corner, it's considered to be an invisible 2. So the index of 2 means we want to create whatever we can to the second power in the radicand inside. Okay, so for 125 is not a perfect square itself. It's not any whole number squared, but it may have a perfect square hidden inside of it. Okay, so I'm just going to list out a few perfect squares along the side. So I'm going to skip 1 because 1 squared is just 1, and factoring that 1 out doesn't really help anything. So 2 squared, 2 times 2 is 4, 3 times 2 is 9, 4 times 2 is 16, 5 times 2, sorry, not 5 times 2, 4 times itself, 4 times 4 is 16, 5 squared, 5 times 5 is 25, 6 squared, 6 times 6 is 36, 7 squared, 7 times 7 is 49, 8 squared, 8 times 8 is 64, 9 squared, 9 times 9 is 81, 10 squared, 10 times 10 is 100. Okay, so I want to see if any of these perfect squares are factors of 125. Okay, so it turns out that 25 goes evenly into 125. 5 times. So I'm going to rewrite this radical as the square root of 25 times 5 and then n. Okay, so I'm going to have to split up the 125 into 25 times 5. And so the reason I would do this is because, as I just showed, 25 is 5 squared. Okay, so now I have a term which has an exponent matching the index. So that allows me to take the base outside in front as a coefficient. Okay, so again, this whole term is gone. The exponent does not go with it. It gets used up. But then I have this 5n left over. Okay, and then again, we usually don't put the 2 as the index. I just showed it to match the exponent. So here would be the fully simplified answer for problem 1. Okay, problem 2. So we have 5, 12. So there's different ways to do this problem. So I'm going to look for something that goes into 5, 12. Okay, so 36 does not go into it. 64 does go into it. So maybe I'll rewrite 512 as 64 times 8, and then I also have the k squared. Okay, so I can rewrite 64 as 8 squared. Okay, and again, when it's a square root, the index is the invisible 2. So matching the index to the exponent, I see I can take an 8 outside, and at the same time I can actually also take this k outside, right? Because this k has the correct exponent of 2 to match the index. Okay, so on the outside I have this 8 and this k, and then I still have a square root, and I still have an 8 on the inside. This one did not get taken out, but I'm actually not fully simplified yet because 8 has a perfect square hidden in it. Right? 8 is equal to 4 times 2. And 4 is 2 squared. Okay, so I can take this base of 2 outside to join the 8k. So when you take a new term outside, it multiplies what's already there. So 8k times 2 is 16k. You do not distribute it to both the 8 and the k because the 8k is all one monomial. There's no plus or minus going on. So 16k as the coefficient on the outside, and then we have the square root of just the left over on the inside. And again, the index of 2 we don't really need to write. Okay, here we've got 512 m to the 4th power, and we're doing the cube root of that. Okay, so this is a cube root. It's not a square root anymore. So this perfect square list is no longer useful because our goal is to make things to the 3rd power, not to the 2nd power. So I may make a new list over here. So again, I skip 1 because 1 cubed is still 1. That's not really going to change anything. 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3 is 27. 4 cubed, 4 times 4 is 16. Times another 4 is 64. 5 cubed, 5 times 5 is 25. Times another 5 is 125. 6 cubed, 6 times 6 is 36. Times another 6 is 216. 7 cubed, 7 times 7 is 49. Times another 7 is 343. 8 cubed, 8 times 8 is 64. Times another 8 is 512. Okay, so in this case, the 512 is directly 8 cubed. Now for the m to the 4th power. Again, my goal is to match the index of 3. So if I've got 4 m's to work with, so I'm going to use 3 of them up to form a group of m to the 3rds. And so I started with 4, I used up 3 of them, I have a single m left over. Okay, so now I can take this base of 8 outside, and I can also take this m outside, and this one does not get to move outside because its exponent is invisible 1 and the index is at 3. Okay, so on the outside we have 8m, and then we still have the cube root, and then we still have this m left over. Okay, over here, we're back to a square root. So looking at my list, I want something that goes into 80. So I know 4 goes into 80. Right, so maybe I'll rewrite 80 as 4 times 20. Okay, and then m cubed, again, my goal is to match the index of 2. So instead of m cubed, I'll write m squared, and then I have 1 extra m. And then same thing for the n cubed, I use up 2 of them, and then I have 1 left over. Okay, so 4 is equal to 2 squared. Okay, so let's take everything out we can at the moment. I can take a 2 outside, I can take an m outside, and I can take an n outside. Okay, so 2mn all goes outside. And then I still have the square root of 20mn. Okay, so the m and n are done with. Right? Those have exponents of 1, so they can't match the index of 2. But the 20 actually I could split up further. 20 is still divisible by 4. 20 is 4 times 5. Okay, so this time I'll just write 4 as 2 squared. So 20 is equal to 2 squared times 5, then I still have the mn. Okay, so that means I can take 1 additional 2 outside to join what's already there. So again, I multiply, so 2mn times an extra 2 means the outside is now 4mn. And then what I have left in the square root is 5mn. Okay, so now I'm going to jump to maybe something over here. Okay, so this time I have a 5th power, so I need to create something to the 5th power on the inside. Okay, so I'm going to make a list of things to the 5th power. Again, 1 to the 5th power is just 1, that's not helpful. 2 to the 5th power is 32. 3 to the 5th power is 243. Right, so that's already bigger than what I have, so I'm going to have to work with the 32. Okay, so in this case, 64 can be 32 times 2. And then we have the a cubed b to the 4th c squared. Okay, so 32 we know is 2 to the 5th power. And because the 2 has an exponent of 5 matching the index, I can take this outside. Okay, so this time that's all I can do, because the 2 now has an exponent of 1, A has a 3, B has a 4, C has a 2. None of the things inside has enough exponents to match the index. So this would be the fully simplified answer. Okay, and so one last situation, if I jump to problem 9. So this time we want something to the 7th. So 2 to the 7th would be 128. So let's see, does 384 get evenly divided by 128? Yes, it does. Okay, so okay, now for the k's, again, my goal is to make k to the 7ths. I have 14 to work with, so I use 7 of them up to make one group, but 14 minus 7 means I still have 7 left over, so I can form another group. Okay, and again, 128 is 2 to the 7th power. Okay, so now I take everything I can outside. 2 to the 7th power, take the 2 out, k comes out, and this other k also comes out. So remember, you multiply all these things coming out, so you have 2 times k becomes 2k squared, and then left over you still have the 7th root, and on the inside you still have this 3. Okay. And now for a division problem. So, this one's not written like a fraction, but the entire thing in parentheses gets divided. So you could rewrite it as a single fraction. Okay, but then because this denominator is a monomial, meaning there's no adding or subtracting going on, we can now split this up into 3 separate terms. Okay, so the first part of the numerator, x to the 4th y, that gets the denominator of x squared y. Then we have the minus sign, and then the next part is x cubed y cubed z, and that gets the entire denominator. And then keep the plus sign, x to the 4th y squared z over x squared y. Okay, so now we can reduce each part separately. So over here, y over y cancels out, and then I have x to the 4th over x squared. So x to the 4th is x times x times x times x. The denominator x squared is x times x. So it looks like I can reduce 2 x's from both numerator and denominator, which leaves me x times x in the numerator, or x squared. Okay, so I just show that this goes away, and this becomes x squared. Okay, so everything else went away. So it's x squared over 1, or just x squared for this term. Over here, similarly, so when you get comfortable, you don't need to write it out this way. Right, so I've got x times x on top, and just x times x on bottom. So 3 on top, 2 on bottom, get rid of 2 from each, that leaves 1 x up top. The y's, you've got 3 y's, y times y up top, only a single y on bottom. So when you get rid of 1 from each section, you start with 3 on top, you get rid of 1, now you've got y squared left over. And the z has nothing to cancel it out, so it remains in the numerator. Again, the denominator is technically a 1 because everything gets canceled out. But over a denominator of 1 doesn't need to be written. Okay, so finally, x to the fourth over x squared. Again, get rid of 2 from each, so it goes away from the denominator and you get x squared in the numerator. Y squared over y, get rid of 1y from each. So this goes away and this goes away. And again, nothing to cancel out the z. So we have x squared times y times z.